Hello math students, we're going to look at vectors today, and this is an introduction, so if you already know quite a lot about vectors, it might be better to skip to the second one, but if you don't, this should be quite a useful intro. So what things do we need to know kind of before we approach this topic? Well, just a refresher, you all hopefully know that if I use the straighter tool, if I have an axis, a system of coordinates, and I choose to place a point in these coordinates 2, 4, then I can write that in coordinates as 2, 4, right? Where the 2 is the x-axis, usually, can be something else, but usually, and the y is the second number. So the first number represents the x, just out of position. We know that because it comes first, it means the x, and the second one is the y. And so in vectors we have something similar, but to do with column vectors, vertical, I guess. But we'll go into that in a second. That's one thing to remember. And this is normally used when you're going to plot a coordinate, like here. While in a vector you have a slightly different idea, even if you want to do it in 2D, and a similar thing to that, a similar layout of coordinates with x and y and everything. With vectors, sometimes instead of a coordinate, what you want to have is like an arrow. Actually, I'm going to use a straight tool. An arrow that indicates the direction of the vector, and that arrow could point from the 0 to the location also 2 on the x and 4 on the y. But in that case, there will be two ways of writing that vector. One of them is a horizontal way, which is, if we label the vector, let's say that this is vector A, then the vector, you could write it like this. 2, well, without the brackets, in the usual notation, you could write it as 2i plus 4j, where this means a component of 2 in the direction of I, where the distance along this axis is actually xi, where x is the coordinate, the 2, and I just tells you what direction it is going in. So now x becomes the size of the vector in the I direction, as opposed to x being itself a direction, and y becomes the size of the other one. So there's your y and there's your x. In other words, the general form for this would be xi plus yj. That's kind of how we think about vectors when it's to do with directions like this. And the other way of doing it, which I prefer, actually is a lot faster, but you need to know about both, is you just say 2 and 4. And that vector 2 and 4 means that the x direction is a 2 and the 4 direction and the y direction is a 4. And so really the position tells you that that's talking about I, and the position of this guy tells you that that's talking about j. And the number in it tells you the size. So the number is your x, and here the number is a 4, that's your y. In other words, the general form for this guy, instead of this here, this was the general form for that type of vector. The general form for this type of vector, which is called a column vector, would be this, x and y. Okay, where this is the I direction and this here is the j direction. You can have them in 3D also, where you have x, y, and z, and here you would have I plus yj plus zk. Right, I, j, k, that makes sense. This is just alphabet, and x, y, z, also from the alphabet. So those are kind of the two types of notations that you can get for vectors. One of them we call the standard form, like this one, and the other one is the column vector form. Okay, so what kinds of things do we use vectors for? They're super useful, but especially in physics and in engineering and things like that, we just use them for things that have a direction, as you can see here, that has a direction and a size, so that what we call the magnitude of the vector is the length of this guy here He has the size, the magnitude would be equivalent to how big a quantity is, like a force. It's one of the things that we use this for a lot. So if we were doing physics with forces, or things to do with velocity, calculations to do with velocity, or what else? Accelerations, displacements, any of all of those, they would all be vectors, because you need to know what direction the thing is going in, not only the size of it. In all of these, it's very important, right? Same with the wind. If you want to know the direction of the wind, if you want to know the properties of the wind, you need to know the force, but also the direction. That's going to influence everything from how you put your sails to whether it's going to be easy to get home or not if you're in a boat, right? Or on an airplane, for that matter. So in vectors, we really care about the direction as well as the quantity, as the magnitude. As the official name is the magnitude. What quantities do you not care for that? Things like temperature. If somebody asks you for examples of scalars, which are the other type of object, then you scalars and vectors are the other one. If somebody asks you for scalars, you need to quote things for which you don't care about the direction. Somebody tells you it's 20 degrees, temperature. Somebody tells you it's 20 degrees, you're not going to ask them, hey, is it 20 degrees up or down? It's just 20 degrees. That's all you care about, right? Same with time. Normally time is, we assume that it always goes forwards unless you're traveling time, which still, as far as I know, you cannot do. And so time is also a scalar. You just, number of minutes that go by. You don't ask for the direction. But if you're talking about forces, velocities, and accelerations, it really does matter if you're going in that direction and the force is going in the opposite, etc. That's going to change all sorts of things. Okay, so what other properties about vectors are interesting? Well, even though with coordinates like this one, that's fixed with relative to an origin. Here's the origin, here's your coordinate, and 2 and 4 are it's like your position coordinates, right? But in a vector, what's interesting about them is that it doesn't matter, the origin doesn't matter. This force here, the 2, 4 force, or 2i plus 4j force, it's going to be the same force wherever you put it. So that force could be there, or it could be all the way over here, or it could be all the way over, I don't know, all the way over here. And I don't care if the origin is here or where the origin is. The vector, wherever you put it, imagine that they're parallel. This one wasn't quite. But it doesn't matter where the origin is. The force is going to always be in the same direction relative to, in the same direction relative to your coordinates, but not starting in the same place. It just keeps its properties of direction. In other words, if I'm over here, then it's got exactly the same direction. The angle, this angle over here, would be the same angle to the horizontal if I draw the vector there, or if I draw it here, or if I draw it here, or all the way over here. So the vectors retain their direction as a property. And we'll see the usefulness of that when we start adding and subtracting vectors, because in that case you can start shifting them around to create shapes that will allow you to calculate what the result will be, and you can shift them around because the vectors don't care about the coordinates, essentially. So hopefully that makes a bit of sense. Other areas where we use vectors a lot, airplanes, the pilot has to know a lot about vectors, like when you're flying and the angle of your wind as the wind attacks on the wings, your engine, how much force you need for that, etc. Like pilots use a lot of information to do with forces. And sports, if you think about sports and all the things that occur in sports and in Formula 1 racing and everything, those designs of those cars are constantly thinking about air drag with forces, and their job is to limit the drag as much as possible. You need to know a lot about forces for that. And in every other sport, you're always going to be dealing with forces too, and the most sort of proficient players are the ones who understand the forces that are involved. Even if they wouldn't be able to do maths with it, they certainly know about how to deal with and manipulate those forces. Finally, this very short intro video, we're gonna I just want to mention that this topic is very good for people who have good visualization skills. So if you're good with art, you're good with seeing things in your head, you're going to find this topic really easy compared with many other topics. And it's quite fun once we get going. So I'm going to leave this video now and I'll move on to the next one. All right, see you in the next video.